Hello, everyone. Welcome to another session of ExpoLab Blockchain Speaker Series. Today is my great pleasure to have Peter DePaulo from Near, and he's going to talk about the sharding of Near platform. And so what's exciting about Peter's background is kind of been everywhere from blockchain to pharmaceutical. He's written code that has been shipped to millions of people. And right now he is the head of the development community of Near. So it's going to be an exciting one. And so without further ado, Peter, please take it away.
Great, cool. Yeah, so yeah, I'll just introduce us actually. So like I said, before we started recording, I brought a friend along, which is Bowen Wang. And he has worked directly and more recently on the actual implementation of sharding that we're going to talk about today. So I'm going to pass the mic to him on the sharding part, and then you can ask him deeply technical questions and he can go even deeper than me. It's been a while since I've written code, just since most of my duties are around community stuff, but just introducing both of us. Bowen, he's been a core engineer at Near for the last 2 years, about 2.5 years. Yeah, he's done a lot of stuff. He's very smart. And then I am not as smart, but I've worked in the developer experience and developer tooling since I started. I was the first DevX hire. And on the side, I work on sustainable behavior. And then I was an early ETH person too. So yeah, if you have questions about war stories in early Ethereum, I can share some of that stuff, which is pretty fun. Things were pretty crazy back in 2017. So let me talk a little bit about Near. I think you guys are aware we're a public sharded blockchain. And if you're not, just so this talk doesn't go straight over your head, we're specifically delegated proof of stake. We're going to get into what that means, specifically the sharded part. We are composed of essentially 3 kinds of people. It's people who are like Facebook MemSQL, Google. MemSQL is a sharded database company. That's where Alex, one of the founders, came from. A couple other folks. The other are like collegiate programming champions, and then there's like previous founders. This is like the broad categories, but in general, we have a very strong engineering organization, and that's been the emphasis. And all of this has been pointed towards this concept of developer usability. So let me, sorry, my keyboard just clicked off. And I want to introduce what we're talking about. So this is kind of like 2 talks smashed into one. The first part, which is like what Bowen is going to talk about, is specifically sharding in blockchains. But I thought it would be interesting looking at what this course is about to kind of zoom out and talk a little bit about crypto as a business. And then also this kind of addendum, which is really just 5 minutes around this concept of behavior in blockchain and outside of blockchain. But we'll get there. You'll see. Hopefully the transitions are not too clunky. And with that being said, we can jump into the sharding presentation. So here we have a blockchain, and I will pass it to Bowen, and he can talk about what happens next.
Yep. Thanks, Peter, for the intro, and I'll hopefully give a brief introduction about sharding as well as our approach to sharding at Near. So as you can see, there is a blockchain. I hope everyone knows what the blockchain is, and with this kind of current generation, or rather things like Ethereum, or even Cosmos. Nowadays, it's what they do is that every single node would validate all the blocks in the system, and if you think about that, it's not the most scalable way of doing things, and there is necessarily a limit to that. So because of that, if we want to get even more throughput than what the current systems can handle, we need to do something else. A kind of natural approach is to have multiple blockchains and each chain can process its own transactions, have its own blocks, and effectively, in an ideal world, we should be able to scale up the throughput very linearly. Peter, next one. Yeah. However, we cannot just smash like 10, 15, 20, or even 1,000 chains together and say, this is a sharded blockchain, because they're a juxtaposition of many different chains doesn't really help because they're not working in a single system. And there has to be some way, some process in which we coordinate some kind of metadata regarding all the chains. And an important aspect of that is how we select validators and how we assign validators to each shard. And for that purpose, there usually is a chain which different protocols call them differently. We call them the main chain. I think Ethereum called them the beacon chain. Polkadot called the relay chain. Cosmos called the hub. Whatever we call it, the idea is that the main chain is responsible for dealing with this orchestration of the overall process, which includes like validator selection and then another metadata processing. This is pretty much the overview of what most of the sharding architecture today in blockchain looks like. And now that we talk about the kind of nice and rosy picture of sharding, there are unfortunately a set of big challenges that comes with sharding. So, as people know that is this 51% attack in proof of work systems, and for Bitcoin and Ethereum, they are not sharded. So if you want to do this kind of attack, you actually need to control 51% of the hash power, which is considered to be very difficult. However, if you actually have, let's say, 10 shards, 10 chains, and then if you want to just corrupt one of them, it actually, the amount of validator corruption you need to do is 10x less, which becomes much more realistic than, let's say, corrupting 50% of the validators. And so one of the ways that we can kind of mitigate this problem is that we pretty much sample the validators randomly. Let's say we have like tens of thousands of validators, and if you want to just and assuming that, let's say, like a small percentage of them are malicious, if you sample, let's say, 100, 200 of them, then the probability that a majority of them is malicious is actually fairly low, or even negligibly low. So we can assume that in that case, this kind of selected set of validators is mostly honest, and because of this, what happens is that when you sample these validators, and then they produce blocks on the chain, and each block is produced from genesis by a set of honest validators, and they each build keep building new blocks on top of it, and because each block is built signed by validators who are mostly honest, we can assume that by induction that this chain is valid, and also this chain is unique. This is pretty much the overview of what BFT consensus does, which assumes that every block is signed by a honest majority to guarantee both that the blocks are valid and also that they're unique. So there are a couple of, so I think we talk about validators getting corrupted and so on and so forth, right? So, but people may ask, what kind of stuff they can do, and there are kind of two big attacks they can perform. One's like creating forks, another which is what we'll focus more on today, and which is also a much worse or much more the attack that would cause much more damage, which is invalid state transitions. And yeah, we will talk more about that very soon.
So just just a quick question. It's kind of I think this is getting very exciting and interesting. So two things at least I guess I have on my mind. One is that how do we deal with cross-shard transactions? So I don't know if perhaps you're going to cover that in the following slide. And the other one I think was very interesting is that, say, if I were to do a random sampling, when I'm constructing the set of validator for every shard, then I can sort of get the same guaranteed as of a non-sharding system. So now the question is, I guess, how do you do that random sampling? And those sampling, is it fixed? Do we create a new sample for every shard for every block, or is it just done once? And so maybe kind of a bit of an insight on that as well. I think that would be very good as well too.
Yeah. So for the first question on the cross-shard communication, yeah, we will get to that I think in a few slides. I agree that the order is maybe not the optimal one, but yeah, and for sampling, yeah, this is a much bigger question, right? It kind of related to how we do distributed randomness, and there is, you can just spend an hour talking about this, and especially if you want to do unbiased if we want to do like unbiased distributed randomness, it is extremely difficult, and there are a lot of challenges associated with that. And we actually have done a lot of work in this front. I think so. Our co-founder Alex has wrote I think a few blog posts on distributed randomness, and how we plan to approach that. I mean, unfortunately, the completely unbiased randomness approach was quite difficult, and it's both in terms of the approach and also in terms of implementation. So we didn't actually take that part. Our distributed randomness validator has one bit of influence over that. So basically, the idea is that you have a randomness seed that is generated every epoch, and then like you use that randomness seed, which is supposedly highly secure, to do this kind of shuffling or like rearrangement of validators and assigning them to shards and things like that.
So kind of putting the question of the pure randomness, yeah, but that's a hard problem. I think that's a well-known hard problem. But assume there is a random function, the pseudo-random function for now. So to kind of get the general flow, if I hear correctly, you said you have notion of epoch. So at every epoch, then you reshuffle and create a set of validator, assign them to the shards, and then I guess they will, after the reassignment, they're kind of responsible for the next epoch. And every epoch, you reshuffling all the validator. Is that that's the general flow?
I think that's also the approach that Ethereum 2 is planning to take.
Okay.
Yeah.
All right. Sounds good.
Yeah. Yeah. Okay. So yeah. Okay. Let's continue on with the current slide. I think I haven't finished that one. Yeah. So yeah. What is an invalid state transition? Yeah. Right. So state transition is pretty much the process where we update. You can think of the accounts in the system. And in this case, let's say we have a transaction that sends 10 tokens from Alice to Bob, right? So what a valid transaction looks like, it would just deduct 10 tokens from Alice's account and then add 10 tokens to Bob's account, right? But invalid state transition, on the other hand, can pretty much do arbitrary things here. For example, it can proceed with deducting 10 tokens from Alice's account, but then just out of nowhere means 990 tokens on Bob's account in addition to 10 tokens that Bob receives. So invalid state transition is almost the worst nightmare that you can possibly have, in a sense that this is even worse than having the entire network stall, right? But because even if you have the entire network stall, like if you find some way to restart it, you can still proceed. But if you somehow invalid state transition gets into the blockchain and it didn't get immediately addressed, then normally what happens is that you have to do a hard fork, and there needs to be some sort of social consensus that take place, and things can get very nasty. So that's why this is something that we want to absolutely avoid. So yeah, so without sharding, it's actually things are easier because if you think about it, invalid state transition now doesn't make sense. The reason being that every node in the network needs to validate all blocks, and if someone tries to do the invalid state transition, that block will just get rejected, and there's and usually this would not be a concern anymore. However, people can still create forks maliciously or by accident, and maliciously creating forks can still be attacked without sharding. Yeah. So what this means is that yeah, as Peter showed the slide here, the attackers they can try to create forks. They can try to build on top of forks and stall the network, and so on. And I think we talked about this cross-shard transaction, and with sharding it actually becomes worse, both in terms of creating forks, and also now invalid state transition becomes an actual possibility that we cannot just ignore. So how does the cross-shard communication looks like? So here we will mostly focus on this async communication model, and I believe this is actually the model that most of the well-known protocols take or will take. Basically, what it means is that if you have a cross-shard transaction, it first will execute on the shard where it originates from, and then after the execution, it will send a receipt to the destination shard to keep executing. Now, a receipt can even go on because it can generate further receipt if necessary, and then it's getting sent to another shard to get processed. Yeah, but basically the idea is that this process isn't really synchronous because you first execute the source shard, and then you send the receipt to the destination shard, and then you execute it there. So as an example here, right? Alice from shard 1 sends some tokens to Bob on shard 2. The first step on shard 1 is that a transaction would first debit Alice's account, and this is executed on shard 1. And then a receipt would get sent, would be created and get sent to shard 2. And now on shard 2, in the next block, that receipts get executed, and then Bob's account is credited.
So if I may ask, can you go back 2 slides? So can you just explain the sort of the flow here? Because that seems to be an interesting. How do you follow this envelope?
Right. Yeah.
What is the starting point?
Yeah. So as I said, right? Maybe that was a bit fast. So what happens is that let's say you have some transaction, right? It originates in some shard, and then what happens is that it first is executed in that shard. And then this transaction, if it's cross-shard transaction, it will create a receipt with all the necessary information it needs to send to the destination shard. And
so kind of, if I were to read this graph, I just want to kind of also follow the graph. Am I reading, is the time going from left to right or right to left? Where is the genesis? Where is the first block?
So the arrows is pointing like to older blocks, basically. So
time is proceeding from left to right, and basically you can think of the arrow as essentially the reference to the previous block's hash.
Oh, I see. Okay,
yeah.
so
sorry, that's a little confusing, I realized.
Yeah. Okay. So
because
from
there are
left
different
to right,
arrows as well. Yeah.
Sure.
Yeah.
Okay. So the first envelope is on the left side, is coming from that top right corner. So that's the first shard, and it gets created on the first shard, first block. Then the envelope gets created, goes to the second shard, and then, or I guess these are different transactions. How many different transactions?
Yes, there are different. Yeah.
Yeah,
these
just
are
to clarify.
illustration of different transactions.
Exactly. This is just an illustration that things can get extremely complicated, because if you look at, for instance, state on, let's just call the top one shard 1, what would be happening is some transaction is going to change state, then a cross shard transaction is going to shard 2, but then in block 3 in shard 1, a cross shard transaction is also going to shard 3. So it's just a demonstration that in an asynchronous system with multiple shards, you have to deal with a lot of complication. And not only that, you have to sync state, like you have to be very diligent in how you think about how state syncs. So
I see.
And
at
also,
what point?
Sure,
go on. No, go on.
Yeah. So and also this illustration only shows maybe like one hop, right? But in reality, it can be more. It can, you have a transaction originates from shard 1, and then it sends a receipt to shard 2, and then it executes there, generates some further receipt, gets sent to like shard 3 or shard 4, for example.
And just sorry, if you can go back again, I had 2 more questions on that. So how often do you also go to these pink shards? So after every block you created, you timestamp it?
Yeah. So this actually. This pink, this isn't a shard, right? This is.
I mean the beacon chain.
The main chain. That's actually an interesting question, because it depends on what the protocol does. So what often happens is that those shard blocks would get cross-linked to the beacon chain every once for a while, and that is usually a way to avoid the damage caused by forks on the shard chain, because basically what the forks tries to do would respect the blocks that are linked back to the beacon chain.
I think one helpful mental model for the pink chain, the main chain, or the beacon chain, is to think of it as like a meta layer of computation, because we're doing all of this stuff like validator rotation and then validating cross-shard transactions and validating blocks and validating headers. All of this stuff requires a really secure place to run, right? You don't want it to run in some centralized place. Otherwise, it defeats the entire purpose of the blockchain. That's what the pink chain does. The pink chain is not actually processing transactions just like a shard. The pink chain is like this sentinel that's saying like, okay, making sure shard 1 and shard 2 are good, making sure these headers make sense, right? So, and like Bowen said, it really depends on the chain, on how frequently it's updated.
Yeah, I think that is a really powerful idea. I think this is probably one of the most powerful usage of permissionless setting in my mind. I think it's really powerful. One last question. So now if you have this cross-shard transaction that is happening, and let's say it's 2 shards or 3 shards, what happens is successfully executes on the first shard, but then it comes to the second shard, then it kind of fails. How does the rollback and abort procedure work?
Right. Yeah. This again, I think in the general case, it's quite complicated. I mean, like this is. I mean, I would say like broadly, this is kind of the issue with asynchronous this communication model, right? You can let's say you execute some contract on one shard, and then it generates a call to another shard, and the call there failed or unexpectedly it pretty much you need to handle the callback. Like you like, let's say you're on the shard 1, and then you basically will need to take a look at the result that's coming back, and then process it and do something to like do some further processing like based on the result. And I think this is an issue with asynchronous communication model, and there has been a lot of discussions, research on that. I think because this can potentially lead to some like problems like like locking things just get like deadlocked.
Escrow gets much more complicated, for example.
Yeah, and then that on its own is something that we can just talk for a day. I think a lot of research has also been done. People discuss different ideas like safes, like yonking, And this kind of ideas basically try to come up with primitives that allows you to lock certain results.
However, in specific cases, what I've seen people, at least in people who are designing applications for this right now, and they're figuring out how to architect their state, they're actually just thinking of this just like you would a node application with asynchronous calls that are going to change a record in a database. So in the best case scenario, like Bowen is talking about, the theoretical and general case to solve this for everybody is actually extremely complicated. But in specific cases where you're like, well, I know, I have some linear, I have some procedure. I have like 3 steps, right? And I know that deterministically 3 things are going to happen, right? In 3 steps. Then people can initiate transactions at any given step in both directions, right? So the thing that makes it hard is they'll have to interrogate state, but at least it'll be treated like an asynchronous system, right? We're like, okay, check out the state, good or bad, and then I'm gonna go and tell like, for example, the previous contract or whatever, what happened, good or bad, right? And that would be facilitated through receipts, just like normal cross-site transactions. And like I said, that's for specific cases. This is like application architecture. It's not really helpful for like someone thinking about it theoretically designing the system.
Sounds good. Thank you.
Yeah, I think we were talking about the kind of potential attacks with invalid state transition, right? So let's assume for a second that shard1 somehow get corrupted, and there's a majority of malicious attackers there, and what they can do is that they can create an invalid state transition in one of the blocks, and then they actually go on produce valid blocks, and in one of the valid blocks they create a cross-shard transaction that builds on top of the invalid state transition, and now from the shard2 perspective, they just received a regular transaction, and then they will just apply it, and since it's from they cannot distinguish on the side of the shard1, and they would just happily apply the result. And this potentially means, let's say you actually mint 1 billion token in block B. Now you can just spend them by sending some cross-shard transaction to use them on another shard.
I'm going to make a quick point here because people have asked me this before, which is like, how is this even slightly possible? In case it's not explicit, the transaction itself is inside of block B, but the transaction is gone by the time the block C comes around. So this concept of an invalid state transition, that specific word transition is what's important because it's a transaction that you're validating, not the state itself. So in C, the state looks good to validators. If someone came along and tried to validate that block, they're like, great, everything looks good. And they don't know because they don't see the transition itself. So I just wanted to clarify that little point. So sorry for interrupting. You can go ahead, Bud.
Oh, I think I'm done with this one. Yeah. So, for there are like a number of ideas on how to address this, right? One of the interesting ideas, I think this is what Kadena uses in their kind of chain web. Basically, the idea is that you actually organize shards in kind of this undirected graph, and each shard is connected to a few, or I mean, by a few, I mean really a small number of other shards. And you can only do cross-shard transaction to the shard that you're connected to. And the idea is that validators in every shard also validates the shard that are adjacent to their shard in this graph. In this example, right, if you understand transaction from shard1 to shard2, and there is invalid state transition, validators on shard2 also would validate, the blocks on shard1, they would have caught this invalid state transition. But yeah, now the problem is that if single shard is corrupted, right, it's kind of fine. But now if there are multiple shards that gets corrupted, we kind of get back to the original situation. Let's say here both shard 1 and shard 2 are corrupted. Then if there's some invalid state transition in shard 1 happening, it somehow just go through from a chain of transaction or receipts, and then it eventually gets to shard 3, but shard 3 doesn't actually validate anything in shard 1. So from its perspective, it cannot know that some invalid state transition happened there. So there's still, this attack vector still exists, although it's kind of mitigated. So this is actually what most of the protocols today use, in one way in one form or another. So basically, Fisherman is this idea that there is this separate group of people whose responsibility is to try to figure out whether such invalid state transition happened in some shard. Usually, what they do is that there are some fishermen associated with each shard, and they would just be looking out for. They would be applying every block as well, and they would look out for this invalid state transition. When they see such things happening, they would submit a challenge, and if the challenge is successful, all the validators in the shard would get slashed, and this is a pretty powerful way to prevent invalid state transition from happening, even if a shard is corrupted. Yeah. So
to kind of just understand, let me just ask one more question on this. So this is really the case is that the invalidator said the child in shard 1 was probabilistically end up to be bad. So the block that was generated in B, it has, it's invalid. So we're trying to periodically somehow be able to cross-check the other shard, making sure even if they hit, they get unlucky and they had bad invalid validator, somehow it gets identified as time goes on.
Well, no, it's rather that there would be some fishermen that's associated with shard 1. They would just they would just spot that there is invalid state transition happening in that shard, even if every single validator in that shard is corrupted. I mean, normally, if not every single one of them is corrupted, some validator would themselves submit the challenge. But let's say, for some reason they are entirely corrupted, then the fisherman kind of exists as a separate entity that can submit challenge and
so
and get the validator slashed. Yeah.
I want to add just that this is triggered anytime headers are being sent from one shard to another, which is the representation of a cross-shard transaction, right? So anytime there's a cross-shard transaction, a fisherman who's, also a form of validator, right? Some validator puts on their fisherman hat, and then they're going to go during this challenge period and actually validate the state.
So then so every time there is a cross-shard transaction, then it invokes checking the other shard to make sure everything has been fine recently. Is that?
Well, it's more like it's waiting. There's a kind of confirmation period for which people can submit challenge, and if no challenge is submitted during that period, then it's considered fine.
But so this fisherman now, this invocation coming from the shard 1, yes? So there is a good entity in shard 1, is trying to do, it's constructing, I guess, the Y is being constructed, or
no, the challenge is basically a proof that there was a invalid state transition. Like basically, it shows that in block B, a invalid state transition has happened. This usually comes in the form of some state proof, basically a proof that the state transition there is invalid.
Right. So shard 2, they will try to invalidate block A and B, and then they figure out block B is problematic.
So well, this doesn't show the entire picture. It basically the challenge will get processed on the main chain as well. So their they would basically mark that chain as mark that block as invalid, and then it will roll back entirely to what happened to the block that comes before that.
And how many of these challenges need to be solved before I can be certain that all the data in shard 1 up to D are valid? Is it just,
I mean, there is, so basically you're not, like, it's not that you're processing all the challenges, it's mostly you're waiting for confirmation, right? If there's no challenger for a period of time, then this block is considered fine. But otherwise, if something happens, if some challenge pops up, then it needs to be processed. It's not that challenges are sent for every block.
So for example, this sounds kind of resembles it like a Bitcoin, is that you kind of have to wait up to 6 blocks before something gets settled. So the settlement period here is that if you wait for long enough and then there's no challenge being raised, then you can kind of be rest assured that what you have is settled. Is that?
Yes.
Okay. And is there sort of a time limit? Is this based on time, based on blocks?
Usually it's based on number of blocks, and I think different protocols use different numbers for those things.
We use 3. It's 3 blocks to finality.
Well, no way. Actually.
Oh, not for the challenge period.
Yeah.
All right, sounds good.
Cool. All right.
Yeah. So with all that, there still is kind of a problem, basically, that in order to even do challenge and also perform a lot of other things, you actually need to actually know the block, right? So an interesting attack is that since not every validator validated every shard, what's if some malicious validator in some shard, what they can do is that they actually produce a valid chunk or valid shard block, and they send the header, let's say, to the beacon chain, and people on beacon chain, they can validate that the header is valid, which it is because the block is valid to begin with. But the problem is that those validators, they withhold the block from other validators. So basically, they would try to not send this data to other validators, and what happens is that let's say you are actually performing some service in exchange for tokens. And from other shards perspective, if let's say if the header of B gets included, then that block is valid. And for example, then you can maybe you provide the service, but then the problem is that now you cannot actually build on B because B is not actually available. And it depends on the kind of implementation here, but you either that shard would just get stalled, or more realistically, what happens is that you just abandon that block and keep building on A, and effectively this would become a problem because you effectively you kind of attack the network, or someone gets scammed, and this can get very nasty. And yeah, this is just basically to iterate what I just said, right? Because main chain cannot actually validate all the shards, and they can only validate headers. But the problem is that sometimes if header is valid, it doesn't actually imply that the block is actually available. So that can cause this problem with data availability.
So just one more question. So what if something that has been written into the beacon chain then gets invalidated? So do we need to go back check? Do we write the compensation? How do we fix that?
Yeah, so it depends on why it's invalidated, right? So usually the beacon chain you can think of as having like a very good security. Like of course, if there's some fundamental assumptions broken, let's say you actually have more than 1/3 malicious validators, then there is pretty much like undefined behavior, like anything can happen, and we usually do not consider those scenarios because if the fundamental assumption of BFT consensus is broken, then I mean, like anything can happen basically.
So I meant not the main chain itself. Is that one of your shard, like let's say your example that you had, the shard B was invalid, but it managed to write its state to the main chain, and then after some point it realizes, well, shard B the block B was invalid. It rolls back, but does it now have to do any rollback on the main chain, or how does it kind of retract it from the main chain, or how does it reflect that on the main chain?
Right. Yeah. I mean, I think here it depends on the implementation. And in one of the scenarios, you could just simply stall the network. And in other implementations, for example, yeah, it could say like, that's you could figure out ways to, let's say, like, that block somehow invalid, and then everyone just build a new block on top of block A, and then basically just discard the block B, and it can get into problems. It depends on like how you cross-link things, right? If B, for example, somehow is already cross-linked, then yeah, it can get into pretty big problems, and then like maybe you have some rules on the beacon chain on how to roll that back. But yeah, this whole thing as I said, this whole thing can get very very nasty. And
yeah, that gets really complicated, because essentially, I mean, the moment you say I can roll back the main chain, you kind of use the immutability of the main chain, and now it becomes a potential attack. What if one shard is trying to roll back valid transaction? How does the main chain how do you provide proof to the main chain that things needs to be rolled back? And there seem to be a lot of interesting cascading effect that could happen.
Mm-hmm.
So yeah, it seems pretty interesting.
Yeah, it's a good point. And yeah, this stuff is like why on the outset sharding seems pretty straightforward when you draw a bunch of squares and like lines between them. But then when you get into actually all of the different problems that you can run into, yeah, it's lots of cascading stuff that you have to keep track of, right? So it's a fair point.
No, it's a very interesting, challenging problem.
Yeah, so kind of the solution that to data variability, I think both us and also Polkadot uses is that we have this, we use erasure code to basically divide a shard block into a lot of different pieces, and we send a piece to each of the validators. The idea is that let's say basically a small amount, let's say 1/6 of them is sufficient to reconstruct the origin data, and the idea is that when the block on the main chain is created, the block producer will not include a chunk if it does not have the chunk piece or the shard piece from the shard block producer, and this basically kind of is a way to make sure that we can like even if the shard somehow is invalid, not invalid, it somehow tries to withdraw their data, then then their pretty much their block would just not get included, and also if somehow validators there are offline or like for some reason lost their data, you can also reconstruct its data from other validators in the system. And here it's basically shows that for each of those pieces, we actually construct a merge tree for all the pieces, And for each piece, basically, you can prove that, oh, this is actually an authentic piece from the original block, because you can because the Merkle root is actually included in the header, and you can actually verify against it. Yeah, and I think here is we'll just go through a list of the famous protocols, I guess, and then see what they. Well, I think most of them are sharded in one way or another, and we'll look at their approach. Yeah, so Cosmos is basically this. They have this hub and dome approach. So basically, hub is you can think of the beacon chain, the main chain that does this orchestration of validators, and each zone. So Cosmos zones are highly heterogeneous. Zones can pretty much be anything, and it's up to the zones to guarantee, to figure out the validators inside the zones as well. Yeah, and there's this thing called IBC that allows communication between zones. So this is kind of similar to the cross-shard communication that we'll talk about. But I think at this time, IBC is still not live yet, because it's actually quite challenging. Even to make sure that cross-shard communication works in a homogeneous system is already quite difficult, as we see various challenges rise with that. Making sure that you can do this across two very different chains, it's just even harder. And Polkadot has a kind of similar model in a way. They have this relay chain and they have parachains. Relay chain is basically similar to Cosmos hub, and parachains is similar to Cosmos zones, but not exactly. So Polkadot has shared security where Cosmos zones should bring their own validators, but in Polkadot the validators are shared between across the system, and actually I'm not super familiar with actually I would say I'm not very familiar with either of those. So I would not try to say things that I that to comment on things I'm not familiar with, in case that I just say something that's completely wrong. So yeah, that's pretty much what I know about them. And yeah, Lidica is kind of a different example in that they don't actually shard state; they only shard processing, and this is in a way very limited, because when you have cross-shard transactions, it can get very slow, and it's not actually utilizing the full power of sharding. And Ethereum is also quite complicated due to this upgrade that they need to do from proof of work to proof of stake, and the architecture is mostly similar to what we talked about before. And they have beacon chain, they have shard chain, and the virtual machine is basically what's the kind of state transition is happening in. It's this environment where you execute transactions and then you perform the state transition. Yeah, and our design is our design is kind of similar to Ethereum in a way, but not exactly. I think this picture actually doesn't do us a lot of justice. Well, so basically we don't have explicit shard chains. We have this thing called chunk that is sort of a shard block that's similar to Ethereum shard blocks, but basically the idea is that we don't actually explicitly maintain shard chains, and we only have kind of this main chain that's responsible for the orchestration. The idea is that you just get rid of a lot of this overhead complexity with shard chains, right? Because if you were to maintain a shard chains, the problem is you can have forks. You can you need to handle how those shard blocks get linked back to the main chain, and as we have talked about, there's a lot of complexity associated with that. Yeah, so that's a kind of design decision that we took kind of early on to reduce some of the complexity and make it just easier to build.
So kind of just a little bit more context. I think these are, I mean, you're highlighting one of the key sort of sharding protocol in the industry, but just kind of from our lab, ExpoLab. So we also have been doing sharding for the past 2-3 years. And so we have 3 main line of work. One is called by shard. So in there, we look at all isolation level and weaker and to the stronger serializability, all the way to snapshot isolation. So we look at like a traditional database, but different isolation semantics. So there is sort of a plug and play platform that allows you to experiment with 18 different sharding protocols. So that's one thing we've been doing. The other one is we've been working with Radix on a serverless protocol. And so there is a whole different flavor of sharding that we've been exploring in partnership with Radix. And the third one is, again, something just kind of in-house, is the sharding protocol that we've been working on in terms of evaluation of it, without going into its sort of technical details of it. It's been sort of also very exciting. So we're able to scale it to globally to over 500 validators, 500 replicas, and sort of peak performance about 1.2 million transactions per second in ResilientDB. So ResilientDB is our blockchain fabric. So that's another very, I think, very related piece of work. We don't have this hybrid model that you're focusing on with this main chain and the shard chain. So I think that's a really interesting design that we haven't explored yet, but there seems to be a lot of interesting similarity as far as the sharding concerned, and some of the problem we talked about, the cascading of the rollbacks and how do you ensure that something is executed atomically, even if it spans tens of shards, and well, if it needs to be rolled back, it will be rolled back atomically, sort of analytically sort of proven that. So I think that's probably some follow-up conversation we could have, which seems to be very interesting. Since you were covering the rest, I thought maybe mention that as well too.
Yeah, thanks. Actually, I hadn't heard a whole lot before I saw the stuff on the lab about Radix, so I actually read a bit about it, which is cool. Yeah, so thanks for sharing. Yeah, ResilientDB is quite cool as well. Yeah.
Thank you.
Yeah, just the last couple of slides on sharding are just a couple of details that are just differences between Ethereum Serenity and Near, primarily like the finality gadget. Yeah, Bowen, did you want to add any other stuff on this or
I mean, not really. It's
okay.
Yeah, it's
cool. Yeah, then I can take it from here. Thanks very much, Bowen. That was like really good. Fantastic exploration of sort of some of the things. So I just want to take a few minutes. I'm glad we interspersed questions. Before, yeah, well, let me just say a couple of things there. I mean, it's written on the slides. But yeah, fundamentally, the core difference between Ethereum, Serenity, and Near is that we have a different and novel model of consensus called Nightshade, which I didn't write here, but and then our BFT-like finality gadget is called Doomslug. And so we don't really have time to dig into the really nitty-gritty details of each of these things, but I linked at the end of these slides, and I think you guys have a copy of them. If you want to go and read more about them, you can read the white papers, and then we have some more friendly explainers on our blog as well. If you're interested in this stuff, exploring actually the differences between Doomslug and then BFT and then PBFT. So that's something worth noting. And then, yeah, this is just fast finality is shorthand for Doomslug, which is I think pretty cool. And yeah, so I want to talk briefly. Well, actually, sorry, before I move on, do any students have any questions about sharding at all or in general? Okay, I'll take that as a no. But we might have some time at the end for a discussion as well. So I do want to talk a little bit about pulling way back on this, right? All of this stuff exists for a reason, right? Like, and if you think about the progression of blockchain overall, we have these proof of work blockchains that emerged, and then proof of work's not fast enough. So we created proof of stake. And then it's like, well, proof of stake aggregates wealth. So what about delegated proof of stake? Okay, well, delegated proof of stake is like not quite fast enough. So we have sharded proof of stake, or sharded delegated proof of stake. And it's interesting to look at just like push the pause button on all of like the feverish technical details of these progressions and think about like how this stuff is actually secured fundamentally at a very fundamental first principles level, and B, what is it trying to accomplish? So right now what it's trying to accomplish, I think, is actually, even though blockchain feels like it's progressed quite a lot in the time I've been involved with it, it's only a couple of years old. It's only a few years old fundamentally. And programmable blockchains were really invented in 2017. And it's only 3 years, I mean, it's 3 years from that time. We're in 2020, I mean, approaching 4 years. So I want to make this point to the people specifically in this class. You guys are in an actual really interesting position in time, which is that you are early to a new technology in which the business models and the way that these organizations are going to come together have not actually been fully fleshed out. Right? So I just wanted to plant this in your head that if you have an idea that doesn't look like an organization, or if you have a project in mind, I know you guys are working on projects right now, it's really easy to sort of write those off as just strictly academic, or just saying like, oh, I'm just a student, I'm not necessarily capable of working on something big. But I promise you that the big ideas that are going to be like taking over the world in a few years look like small ideas now. They look like things that are unrecognizable as big ideas. And one piece of this, which is a new idea because of staking, I wanted to sort of introduce to you, which is the concept of, I call it an infinity machine. So because of staking, if you were to create an application that is paid in some protocol that uses staking's native token, you could write a program to restake the tokens that you're paid in, right? So you make an application for people, a DApp, a distributed application. I saw you guys were exposed to some concepts there, and you're charging people automatically, and then you restake that money. You probably haven't thought through the economics of how you can actually create a successful business or a successful side project out of this. And I wanted to show you that. Basically, I unfortunately didn't write all of this stuff down, but I wrote an essay on this, and I'll be publishing it in the next couple of weeks. It works such that in a conventional proof of stake network, if 70% of the network's tokens are staked, you can expect basically 6% inflation, meaning 6% of tokens will be returned to the people staking in the form of block rewards. What that means is if you create something that ends up garnering 1 million tokens, let's just say arbitrarily, which would be roughly 8,435 people paying 10 tokens per month. So you bear with me on the math, but you get there in a year, you get 1 million tokens. You could then have a return from that at around 60,000 tokens per year, right? For 6%. Really easy math. The reason I bring this up is because if any of you are inclined to start businesses, the way that it works is you go to some investor, they give you, let's say, $1 million for some stake in your company. And the way that their economics work out is that they've invested in, let's say, 100 companies with the expectation that 90% of them are going to fail, right? And then a few are going to succeed and become something like Airbnb. I just want to make the point that proof of stake changes that model in a dramatic way, that somebody in a country outside of the United States, someone outside of Silicon Valley, could come and build a product, and they could publish it and people can use it. And then by restaking the rewards, they can live indefinitely off of just staking rewards, even if their product is no longer successful after a few years. So it's just something to think about. And then the last piece of this, and I'll stop for questions after this slide, is that the first generation of blockchains were secured by proof of work, which was actually cryptography. The second generation of blockchain, the second generation too, right? Proof of work. The third generation of blockchains is proof of stake. They're actually not secured by cryptography. That facilitates the security, but it's not what actually secures the chains themselves. They're secured by economic models that try to predict people's behaviors and planting incentives. So if you think about why we need Fisherman in a proof of stake sharded blockchain, it's because what we're trying to do is give someone a competing incentive that is comparable to the malicious behavior that might make them rich, or they might take down the chain, or whatever their malicious incentive is. So fundamentally, predicting behavior is very hard. And the fact that we're able to do it in a way that actually secures these new protocols that actually are locking millions of dollars of value is very, very interesting. And an even interesting meta point is that essentially what these economic incentives are doing, what we're trying to predict is market behavior. It's actually behavioral economics. And blockchains are inherently markets. Any blockchain with a native token is itself a network, and a network with an economy is what a market is. I mean, I don't want to argue about markets right now. So that's just something that I wanted to expose you guys to that, like I said, didn't really fit into the sharding presentation, but I would imagine not many people would have covered that. You know, all of this stuff seems really complex technically, and yes, it is. But at the root of it is actually human behavior, predicting the psychology of actors in a network in order to secure the network itself. And I think that is fascinating. So that's it. Yeah, and then behavior doesn't relate to crypto. Just like, I know you guys are in college, and I imagine when I was in college, if I had to like go to a Zoom class and this is how I was exposed to class, it'd be kind of sad. Maybe you guys like it. Maybe you guys are homebodies. But you know, it's a challenging time. You guys stay healthy, take care of yourselves, find, you know, talk to your friends. I know like probably lots of people have already said this to you, but don't forget the human element of all of this in this COVID time. Hopefully we'll have a vaccine. We'll move on past it. But yeah, that's just what I just want to put this in there as like a little cherry, like, please take care of yourself, guys. And then lastly is just, yeah, thanks everyone for listening. Thanks again to Bowen for giving the presentation on sharding. And thank you, Mo. Sorry, I don't know if you're called, I don't want to mispronounce your name. Is it Professor Sadeghi? Is that?
All sounds good.
Okay, close enough, Sadeghi. All right. Well, yeah, thanks for inviting Nir here to give our talk on sharding. If you guys are curious or you want to get involved, anyone watching in the recording or anyone currently listening, there's lots of ways to do it. Nir.dev, all of our code is open source, and almost all of our work is publicly discussed. We work through GitHub. Nir.chat takes you into our Discord. You can meet our community. We have lots of people now who are pretty I mean, extremely impressive, actually, working on really cool stuff. If you're actually interested in the implementation, so all of this was really theoretical, you can actually look at the specification that's more up to date, the very specific, the Rust code that implements these things like Fisherman and validator rotation, things like that. You can look at nomicon.io to start seeing the chain spec, and then GitHub, right? If you go to github.com/nearcore, you can then actually like dig into the Rust code. Near.dev, for anyone who wants to build applications, is a great place. We didn't even talk about the runtime. We didn't talk about application development specifically. But if you want to write some apps, near.dev is a great place to start, has example code, and that's where you can get started. You can actually start writing in your browser. We set it up so you can click on the examples, and then there's an IDE that launches. So yeah, that's it. That's all we've got.
All right. Thank you so much. That was wonderful. And
Cool.
I wish to take this opportunity on behalf of ExpoLab and UC Davis. Thank you for this very insightful and engaging lecture.